I will be presenting our work on budget RNNs, which are a neural network system to perform inference under energy budgets on low-power devices. Battery-powered sensors have applications in a variety of areas, such as wildlife tracking and activity monitoring. In this work, we consider a concrete sensor, which periodically collects data over time. The sensor performs inference on these data windows using a recurrent neural network and sends the inference results over a wireless link to a centralized server. This RNN style of inference makes sense in the context of sensors because RNNs are compatible with the sequential style of data collected over time. Battery-powered sensors have a fundamental problem in that their lifetime is finite. It's capped by the size of the battery. To elongate sensor lifetime, one key strategy is to supplement battery power with energy harvesting units. These units capture energy from the environment and use it to recharge the battery. This allows a single sensor to operate for longer than one battery charge cycle. While renewable energy allows for sensors to elongate their lifetime, energy harvesting is inherently unreliable. Harvesting is dependent on environmental conditions, and there are often cases where the environment itself has no available energy. Despite this unreliability, device operators desire reliable lifetimes, especially during these periods of no renewable energy. So for example, a device operator may want to guarantee 48 hours of operation on battery power alone. When the starting energy amount is high during these periods of no renewable energy, standard sensor operation is often sufficient to meet energy constraints. But the problem here is that the starting energy amount is wholly dependent on environmental conditions because it depends on how much the battery is recharged during the last charging period. Therefore, it may equally be the case that we start with much less energy than we thought, in which case standard sensor application won't actually meet the energy budget and instead exhaust the energy much, much quicker. In essence, we want to design sensors that can react to these changes in starting energy and elongate their lifetime over the operator-defined window. Just to emphasize this point further, the starting energy is based on environmental conditions and itself controls the energy budget with also the operator-defined window. Thus, we want to specifically design sensor applications that meet energy budgets that are unknown at design time, as many of these energy budgets are only known through the environmental conditions observed at runtime. One way in which we can design RNN-style applications to meet energy budgets through controlling their energy consumption is by employing subsampling. Sensing hardware itself consumes a significant amount of energy, and devices can adapt their lifetime by skipping periodic readings. This strategy itself comes at a trade-off, and that trade-off is in terms of accuracy. RNN inference will work best when capturing the most number of elements, simply because the RNN has the best view of the overall environment. As the collection goes down, so does the accuracy, because the RNN has much more uncertainty about what the environment really is. From a systems perspective, what we have here is a mechanism in sampling that can be used to meet these constraints, but we want to do so with the minimum amount of loss in terms of accuracy that's imposed by fewer or less frequent collection. So to manage this trade-off in the most optimal manner, what we can notice is that RNN accuracy itself is sensitive to which elements the system actually captures. And from this insight, we get the concrete goal of using subsampling as a mechanism to meet dynamic energy budgets, while creating a sampling policy to capture the elements that maximize the RNN's inference accuracy. Existing RNNs have a few different ways in which they can integrate with subsampling policies. The easiest is to integrate standard RNNs with what we call early exiting. Standard RNNs will work by capturing measurements over time and processing them accordingly. But rather than capturing and processing all elements in a sequence, we can skip the final few and create a prediction based on internal memory state of an earlier measurement value. In this case, we don't have to even incur the energy associated with collecting or processing X3 or X4, therefore controlling the amount of overall consumption. One key downside, however, with this approach is that the subsampling policy is inherently inflexible. It's limited to prefixes of the overall sequence, and there's no reason that this is necessarily optimal. To address this problem, we can instead use RNNs with what we call trainable sampling, where the subsampling policy is learned along with the rest of the RNN parameters. This learning process is done to capture elements which in turn will minimize the overall error. For example, we can have a policy which captures element 0, looks at the data and skips x1 to go straight to x2, then captures x3, and then finally skips towards the end. And note that this policy is determined by learning it from data to minimize the overall error, thus giving it the ability to better optimize for accuracy under these constraints while capturing the same number of elements as, say, in the standard RNN. Now, while these situations or these systems seem to have the ability to meet energy budgets, there are actually a few issues with them with respect to the dynamic energy budgets seen in sensors. Starting with standard RNNs, these systems have the ability to alter the energy level and meet dynamic budgets within a single model by simply changing the exit point in the overall sequence. The problem, however, comes in terms of accuracy. The models are limited in terms of how they can sample, and this causes them to oftentimes produce suboptimal accuracy. To address the accuracy point, we have models that exhibit trainable sampling, like phased and skip RNNs, which can support these non-prefix subsequences, but they have themselves their own downside, which is that they need the budget to be specified during training. In essence, these models can achieve high accuracy through flexible sampling, but they don't have the ability to adapt to multiple energy budgets because the policy itself has to be trained to a single energy budget. Thus, within these exact models, systems would need to train multiple different RNNs, each trained for a different energy budget. And this only increases the training time and also can quickly exhaust the memory constraints of low-power devices. Thus, there seems to be a fundamental tension that exists here, where RNNs that find optimal subsampling policies need the budget at design time, but its property is a really poor match for systems that have dynamic energy budgets. In essence, we want a system that can meet or exhibit high accuracy through flexible subsampling, but also has the ability to adjust to multiple different energy budgets within a single model. And we designed budget RNNs to fill this exact gap. Budget RNNs are a system consisting of 3 different components. The first is a novel RNN architecture, the second is a subsampling policy, and the third is a runtime controller. Together, these components create a model which can support flexible subsampling policies, while also decoupling the RNN training from budget-specific information, which allows a single model to adapt to multiple different energy consumption levels. The budget RNN model architecture supports flexible subsampling by applying RNNs to non-prefix subsequences. In essence, this is a generalization on the early exiting we see with standard RNNs. As an example, we can consider a sequence of 6 elements broken up into 2 subsequences where consecutive elements are captured 2 steps apart. In this design, we can apply a standard RNN to this first level of this first subsequence and creating a prediction pred 0 based on only half the data. We can then integrate the remaining elements into a second level subsequence to refine the predictions from that first subsequence and create a second prediction pred 1 of higher quality. And to avoid any recomputation in computing the second prediction, we can merge memory states across these different subsequences through an extra merging gate, therefore allowing us to improve prediction quality without having to compute on a single measurement more than once. This design allows us to control the energy consumption of the system through early exit. And to see how this is done, we can consider a case where we want to save energy. We can do this by using only prediction 0, in which case we don't need to even interact with the second level or second subsequence. Thus, we can save energy by not even collecting or processing X1, X3, or X5. Instead, we get an intermediate prediction based on a non-contiguous subsequence or non-prefix subsequence, thereby allowing the system to achieve higher flexibility while still exhibiting the ability to save energy. Now, a key question here is then how we determine when to select prediction 0 versus prediction 1. And this determination is made by the sampling policy itself. To aid in this decision-making and to allow the decision-making to respond to specific trends in the data, we augmented budget RNNs with what we call halting signals. These halting signals are trained to predict the probability of a correct prediction at every single level. In the sense, they are a general metric trained without reference to any specific budget. So for example, halting signal at level 0 or subsequence 0 is the probability that pred 0 is correct. This gives the sampling policy, which we'll discuss in a second, the ability to have some notion of what the classification accuracy might actually be without actually building the budget-specific information into the RNN training itself. The sampling policy works in a thresholding manner. It defines thresholds for every single halting signal, and at every level asks the question, is the signal greater than the corresponding threshold? If so, the system is confident enough its prediction because the probability of correctness is deemed high enough, in which case it can save energy by taking prediction 0 and skipping the subsequent level. Otherwise, the system deems that the prediction at level 0 is too uncertain and can remedy this uncertainty by integrating more data from the next subsequence. And this, of course, requires more energy in order to do so. Now, the key part of this subsampling policy defined by these thresholds is how we actually create the thresholds themselves. And these thresholds are created in a budget-specific manner. In essence, the thresholds provide a link between budget-specific information of how much we need to conserve, while also integrating information about how we should value classification accuracy or how we can exploit maybe exiting early and still getting the correct answer. The budget-specific thresholds are themselves fit through an optimization process in an offline manner by maximizing accuracy over a set of chosen constraints. And while we're still in this scenario, optimizing at design time over some constraints, this presents a much better trade-off from a design consideration over RNNs that perform trainable policies in a tight coupled manner. For instance, fitting these thresholds is much cheaper than fitting an entirely new RNN, and all that's required to generalize to a new budget here is to fit a new set of thresholds. Furthermore, the memory consideration is much less. If we want to fit a new threshold, or if we want to add a new threshold vector, it's just a few numbers, as opposed to the much higher memory associated with fitting an entirely new RNN. Now, this system as presented here has a few key challenges. Firstly, the fitting process itself, as I mentioned, requires target budgets that have to be specified at design time. This is exactly against the type of processing or the type of scenario that we consider in a runtime environment. Thus, we need a mechanism to generalize thresholds to unseen budgets at runtime. We can do this by linearly interpolating thresholds on the fly from this seed set established during training. This linear interpolation, however, is just a low overhead heuristic, and it's not necessarily the case that halting thresholds in the true energy consumption have a linear relationship. Thus, when we create these thresholds on the fly, they may not actually be able to guarantee that we meet the budget. Furthermore, the optimization itself in an offline manner relies on profiled energy values from the sensor and target microcontroller. And these values may actually differ from what we observed during runtime, and we need a system that's robust to such runtime variation. Thus, we can address both of these through a runtime controller unit that makes dynamic adjustments on the fly. This runtime controller dynamically sets the target from which we derive halting thresholds using runtime energy feedback. So if we have a set budget and we observe some sort of value for energy per sequence, we can compare that to an expected bound, which is based on past performance, and use the corresponding error to set the target value. The reason we use a bound here instead of an expected single value or even pinning this to the budget is that adaptive policies themselves exhibit natural variance that they use in order to get good performance. To see this point further, we can see that if you can take an example of a budget of 500 millijoules over 100 sequences. While this means that we have to have an average of 500 millijoules per sequence, it doesn't mean that we need to have exactly 5 millijoules for every single sequence. And indeed, an adaptive policy might use much more energy on harder sequences, and then on the other side, save energy on easier sequences, thereby still averaging to the same amount, but using the overall allocation to its benefit to maximize performance. Thus, we create this bound to support this variation and then tighten the bound as the time goes on in order to guarantee we meet the budget, while still actually maximizing, or at least allowing the adaptive system to maximize its accuracy. We evaluated the system on 22 budgets across 7 different data sets, which correspond to a variety of sensing tasks. And across these situations, budget RNNs produce the highest mean classification accuracy in every case when compared to standard RNNs, and then also RNNs with trainable skipping, such as phased and skip RNNs. Furthermore, we can compare these results on a budget by budget basis on a single task. And we see that budget RNNs provide massive benefits at these very tight constraints and then nearly meet the baseline systems at the top level, but with no assumptions about what the budget actually is at design time. Budget RNNs provide the best overall solution across the entire range of possible budgets. Finally, we can look at these results in the context of energy and see how much or what budget the budget RNN would need to produce the same classification accuracy as that of the baseline systems. We find that even when operating under 20% smaller energy budgets, the budget RNNs achieve similar accuracy to that of the baseline systems themselves, therefore providing big benefits from the perspective of energy too. Just to conclude here, what we discussed here in this work is a new way of performing RNN inference under dynamic energy budgets on low power sensors. We presented a model that's designed from the ground up to meet dynamic energy budgets and uses a leveled architecture which supports multiple different energy modes without compromising on sampling flexibility. The system itself leverages halting signals in a runtime controller to optimize accuracy under these constraints and outperforms existing RNN solutions on a wide variety of tasks and across multiple different budgets.